Okay, so today's lesson is on 5.6 in your textbook, page 240. It's 8.6, unit 5. Change of state and latent heat. We've talked a lot about kinetic molecular theory this chapter, right? And we've talked about change of state. When energy is applied, something that's in the solid form will begin to vibrate, and the molecules and the atoms will begin to gain more energy and move more, and they'll literally break apart from each other, and they start to separate, which kind of yields the liquid form, right? And those liquid particles, as they vibrate and jump around, they're going to gain enough energy to jump out of the liquid into the gas state, right? Where they are very far apart from each other and have a high amount of energy. So if you think about change of state, and if you think about something called latent heat, which I'll explain in a second, we're going to talk about how much energy is required to heat something, or to change the state, or to basically heat something that's in solid all the way up through to gas. We're going to be able to calculate the total amount of energy involved there. So as you write down, copy down these notes here, I'll just read them along. It says, when you add energy to a liquid, the temperature will go up. That makes sense, right? All of you yesterday in the lab, those of you that were here for the lab, we took a beaker full of snow from outside, and we put it on the burner, and we took the temperature as it was heating. Okay, and the graphs that you made, I just looked at a bunch of those graphs that you made, and they looked pretty good. Okay, and now I'll explain about what a good graph looks like in this case. But we know that the liquid water, as we apply more and more energy to it, the temperature goes up, right? That makes sense, right? Okay. Is there a limit to how much the temperature of the liquid will go up? So if we keep heating a liquid, what's eventually going to happen to that liquid? It's going to, It's going to boil, right? It's going to turn into the gas state. So then it's going to turn into gas. So there is a limit, right, to how much we heat. And this is a little bit of a description here. For example, solid ice, you heat it up, the temperature will start to climb. The temperature will pause. I don't know if you want to use the word pause, but it'll pause at 0 degrees Celsius until the ice is melted. And do you know what? In your graphs, you guys kind of showed that. We started off with snow, and for most of you, it was above 0 degrees. Okay, so there's a little bit of error, maybe in the thermometer, maybe just in the conditions in the lab. But you kind of had points like this where right around 2, and they kind of stayed pretty much consistent. And then I saw there was a huge jump until the water started boiling. And this is what a lot of your graphs looked like. Okay? So if you heat up something that's in the solid form, or snow in this case, when it was melting, and for those of you that have started your observations or put together your observations or remember them, I told you to take special note when the snow started melting and when it completely turned to liquid. And that, I don't know if you can see us now, it's pretty small now in my diagram, but the temperature was fairly consistent in this area. It didn't move too much, did it? When the snow was completely melted, okay, there was a sharp change in temperature. All right, and this is exactly what we would expect. The temperature goes up, but at the phase change, okay, we noticed that the graph sort of leveled out a little bit. And most of your graphs looked something just like this. All right, so let's get back to the notes here. It pauses at 0 or around 0 until all of the ice or the snow has melted. Once this has happened, the temperature starts to climb sharply again, and that's this area. If you were to create a graph of temperature versus time, so here's time down here, and here's the changing temperature, and this is what most of you guys did, you would notice that the graph levels off during a phase change. This is one of the indicators to physicists that there actually is a phase change happening. Okay? So the heating graph levels off during a phase change. And that's what we kind of see here, and when it starts to boil. Now, what did you guys notice about the boiling temperature of your water? It was pretty low, actually, wasn't it? It should have been close to 100. Okay, or close to that, you would have guessed. But what was it for some of you? Do you remember just offhand? 87, 93, 75. Okay, So the temperatures really vary. Now, that could be the thermometer. It could be that maybe, it wasn't mixed real well and you had some cooler pockets or whatever. Remember, the water was boiling from the bottom, so if you didn't take the temperature of that water at the very bottom of the beaker, maybe the average temperature would have been lower, right? But anyways, regardless, yes, it was a little bit lower than we expected, okay? So there are some imperfections when we do a lab, but this general shape of the graph is certainly what we expect. Now, this graph right here, okay, this is a typical heating graph, okay? So it's a heating curve. And let me just explain this as you start to copy this down here. So this is time over here, and heat is added over time. This is temperature. And what we see is, and let's say that this is ice, okay? So I'm going to label this as the heating curve. And I know there's only straight lines. Don't get hung up on the word curve, okay? But this is called a heating curve for water, okay? Now, we didn't take the temperature of solid ice. We started with snow. So we kind of started around this B area right here. All right, but this temperature right here is where the solid starts. As we add heat over time, the temperature of the solid, you see that? This is the temperature of the solid is rising. So this part of the graph is where the solid is being heated. What temperature would this flat part of the graph represent? 0 degrees Celsius. Very good. Does anyone remember what temperature that is in Kelvin? Not 0 Kelvin, no. What is that in Kelvin, you remember? 32? No, that's Fahrenheit. 273. Yes, 273 degrees, not degrees, sorry, 273 Kelvin is the melting point of water, or 32 degrees Fahrenheit. Yes. Okay, good. This is good to refresh our memory. So, the big part of this lesson is this, is noticing that the temperature does not change during a phase change. The temperature doesn't change during a phase change. And I'm going to explain to you why that is in a second. But as we move through this heating curve, you see that this part of the graph right here is the heating of the liquid. I don't want to make this graph too busy, but here is the heating of the liquid. Okay, the temperature is rising. We're applying heat over time. The temperature is rising. What temperature do you think is associated with this flat part of the graph right here? What temperature here? 100 degrees Celsius. Very good. 100. And why is that? Well, because this flat part of the graph, as we've mentioned, represents a phase change from liquid to gas. Okay? So the question is, why does the heating curve flatten off there? Why does it level off during a phase change? Because we didn't stop adding energy, and these notes down here just kind of explain in different words that I'm going to use what's happening. We're not stopping, the heat, right? We're adding heat the whole time, but even in your graphs, you saw that it leveled off there. So what's happening? The energy that we are applying to this substance, that energy is actually going to breaking the bonds between the atoms. Remember I said at the beginning, kinetic molecular theory, as solid, in solid form, when those atoms or molecules have low energy, they're really close together, and they kind of don't move much. But when you add energy to them, they start to vibrate, and they start to break apart. Well, when the bonds between the molecules are being broken, that's where that energy is going. It's not actually reflected in an increase in temperature. The energy is used to break bonds. Okay, so during a phase change, the energy is used to break the bonds between molecules. Okay. Energy in a phase change is used to break bonds. So let me talk about what's happening during that phase change. And just like we have an equation for the amount of energy that's used to change the temperature of something, we also have, and we're going to see right down here, there's a formula for calculating the energy during a phase change. So once all the bonds have been broken, then the energy will start to heat the substance up again and the temperature will change. So once that phase change is complete. But during this time, since there is no change to the overall temperature during a phase change, we call it latent, which that means kind of no change. It means kind of subsurface, hidden away, latent, okay, not apparent. We call it latent heat of fusion, and that is at the melting point. So there's a specific sort of heat that constant that's associated with melting of a certain substance. And there's also a latent heat of vaporization, which is the energy required to vaporize a liquid to a gas. Okay? So each different substance will take a different amount of energy to change phases. Water will take a certain amount of energy to change it from ice to liquid. Iron, okay? Iron will take a certain amount of energy to change it from solid to liquid. Right? If it's a different substance, it has sort of a different different constant. Now, okay, so think about fusion, heat of fusion. That's either bonds coming to atoms coming together and being fused. Okay, fusion is like fused, and so this is talking about solid to liquid or liquid to solid. That's the same point. Okay, so you think about liquid going to solid; those atoms are being fused together in a sense. And vaporization, of course, is from liquid to gas or gas to liquid, back or forth. That's the heat of vaporization. Think of vapor, gas. Okay. So the latent heat of fusion is for the solid to liquid phase change, and the latent heat of vaporization is for the liquid gas. The formula for calculating the energy associated with a phase change, so how much energy is required to change phase, there's a little formula right here. The energy, and they say L because it's sort of like latent heat energy, is equal to M, which is the mass of the substance, times L, which is a new constant that we're going to learn, and that's, of course, these latent heat constants. So latent heat of fusion or latent heat of vaporization. Now, if you think about heat, remember heat is the transfer of energy. So I have a question for you, a little quiz here. Okay, is heat absorbed or is it given off when a substance changes from a solid to a liquid? Is it absorbed or given off? What happens? What has to happen? Solid to a liquid, does it need heat or does it give off heat? It needs heat. Yes, it needs energy. Okay? So energy is put in or has to be applied to change from a solid to a liquid. That makes sense, right? You have solid ice, you need to heat it up to get it to liquid. Okay? Now what about a liquid freezing or fusing into a solid form? Would that make sense that it's the opposite? That it's giving off energy? And actually that's true. It gives off energy when it changes phase. There's a little example. How many of you have ever heard of vineyards or people that have plants with fruit on them, and when it's about to freeze unexpectedly, and these are grapes. That's it. Fine. These are grapes. I don't know if you noticed that. But anyways, have you ever heard of this happening? And like for strawberries or something like that, if there's an unexpected frost that's coming, Mrs. Clark, I bet you know what sometimes happens there. Yeah? Using this whole idea of heat energy giving off and absorbed and stuff like that, sometimes what you can do is if there's an unexpected frost coming, you can actually water the garden really well so that it's very, very wet. Now, why is that? Why are you moistening or wetting a really delicate fruit or leaf, plant? Because when it gets cold overnight, what's going to freeze? What's going to absorb, what's going to freeze? It's going to be the water. The water is going to freeze, right? We know that if the temperature drops, if it's a frost, water will freeze. So in that process, we just said that when a liquid changes to a solid, it actually gives off energy. So guess what? In a sense, unless it's a solid freeze, then we're in trouble. But if it's right around zero, that water that's on the fruit will actually freeze, and it'll actually give off a little bit of heat energy to the plants and the fruit. And so that's the way it can be protected. So that water will freeze and not the fruit, not the plants. All right? So that's sometimes people do that if it's just going to get right around zero and they're kind of unsure. Sometimes you'll see that, and that works. Okay, because it gives off a little bit of heat when something freezes in water, especially. Well, okay, when the ice on the fruit melts, okay, yes, it'll take a little bit of energy, but is that energy going to be sucked out of the fruit, or will it start to melt when the sun comes out? You know what I mean? So it'll take that energy from the sun or just as the temperature rises. But you're right. I mean, if it's a hard freeze, it might suck all that energy out of the fruit and may damage the fruit too. But chances are the sun will come out the next morning and melt that little bit of ice. But that's a good question. Yeah, and the opposite process. That's right. All right, we can probably skip that part. Now, this is the big deal about today. What we're doing, don't get too stressed out here, but what we're doing is we're going to take a look at this heating curve, and for each section, we are going to be able to calculate how much energy is either given off or required at each section. So, for section number 1, so what you're going to want to do, if you drew this graph already, that's great. I want you to label this part right here section number 1. Okay? That's section number 1. And this is what's happening in section number 1. We are actually seeing a temperature change. You see this? The temperature is changing. And so the energy calculation or the energy formula we use is E equals mc delta T. And so this is the energy required to heat up the ice. That's in section number 1. And on this heating graph, this is going to be minus 20. Minus 20 degrees Celsius, or negative 20 degrees Celsius. And so we won't do the actual calculation just yet, but just so you understand what's happening. We can calculate the energy that is required to heat up the ice. And what's the temperature change? Well, from negative 20 to 0 degrees Celsius. So that's this section right here. So that's an E equals mc delta T. And the C that we use, the specific heat capacity, is the C for ice, solid water. Okay, got that? The second section now, we move to the second section. Let's take a look at number 2. This section here is associated with the phase change from solid to liquid. And this is where we use this formula, E equals m times L. So we're given the mass here in the original question. We use the same mass. You see that? It's always the same mass. We use the mass of the water, and L, of course, is this new latent heat constant, and this is latent heat of fusion. Right? So section number 2, this flat part of the curve, we need to calculate the energy that's associated with melting of that ice. So we've got E equals mc delta T for 1, and E equals mL, and that is the latent heat of fusion. All right, section number 3. Section number 3 is the heating of the water. So the temperature is changing. You see how the temperature is changing from 0 all the way up to 100. So we're going to use the E equals mc delta T. There's the temperature change. And that's going to be for water. The delta T is the change in temperatures from 0 to 100, so that's 100 degrees, right? When we heat the water all the way up to the boiling point, it represents a change in 100 degrees Celsius. So that's section number 3. Questions? Yep. Yes, that's right. Steam, water, ice. That's right. So ice has a specific heat capacity that's different from the specific heat capacity for water. Don't change out the T, but change out the C. Yeah, change out the C every time. Right? Now, I think if you look carefully, two of them are pretty much the same. But, is that true? So, yeah, if you look on page 235, right, liquid has a very high specific heat. Ice and steam are almost identical. Weird, hey? That it really takes the same amount of energy to heat ice as it does to heat steam. The same amount. That's amount of temperature. That's pretty cool. Water takes a lot of energy to heat, and that's great. It's good for us, isn't it? Okay. So what section are we on now? Number 4? Section number 4. Here we go. This is the heat or the energy that's involved in what part? In vaporization. Yes, or the boiling of the water. Right. And we go back to E equals ml. But in this case, L is the latent heat of vaporization. And in your textbook, I believe, that's page 242, is the chart where you have those latent heats. So here's a chart here that may not be identical to the one in the book, but it takes a look at different elements, okay, or different compounds. So here's water, right there, and we can see that water, the melting point is at 0 degrees Celsius, and the latent heat of fusion is about 3.33 times 10 to the 5 joules per kilogram. Now in your, yeah, it's exactly the same in your chart there, same units and everything. And the latent heat of vaporization is 2.26 times 10 to the 6. Now if you look at those two numbers, which phase change requires more heat or more energy to change phase? Which one takes more energy? Melting? Boiling? Okay. What do you guys think? Melting? Boiling? Okay. All right. So what you need to do is look at these numbers, okay? So the latent heat. Now this, again, would be the heat required to melt from solid to liquid a certain amount of, 1 kilogram of water. And so this is 3.3 times 10 to the 5. This one here, for the same amount, is 2.26 times 10 to the 6. So it requires more energy to boil than it does to melt the same amount, because this number is higher. Does that make sense? The higher number takes more energy to change the phase of the same amount of substance. Okay, so it takes a little bit more energy to boil the same amount of water than it does to melt the same amount of ice. Make sense? Sort of? All right? Yes. Yes, I can scroll up, yes. Any other questions about the latent heat chart, though? How does what? How does helium melt? Okay, well that's a good question. Yeah. Well, okay. Well, helium. Now look at the melting point. It's a good question, guys. Watch this. Helium. You don't think of helium as a solid, do you? Why? Because helium at room temperature is a gas. It's not even a liquid, right? Helium. Okay. Gas. No problem. So, but there is a point. There is a point where it will freeze from a liquid to a solid. So the melting point is the same as the freezing point. Okay, it's the same point, at negative 269. Now how close is this to absolute zero, right? Negative 273 is as cold as anything can ever get. So helium doesn't freeze very easily. But there will be a point where it'll freeze. So if it's frozen solid, if we have it at this temperature, it's frozen solid or colder than this, then it would take this much to melt it. And this wouldn't, I mean, you know, it's similar, I guess, but it's a little bit lower, isn't it? That's the number. All right, the boiling point, look at this. It goes from a solid to a liquid at this point, and then look at this, it's like 1 degree. All of a sudden it turns to a gas. So helium is a gas from every temperature above this one. So it's a gas pretty much all the time, right? We can't freeze helium pretty much because we cannot really get it down to this temperature. It would be virtually impossible. Now, what about copper? Okay, look at the melting point for copper. At room temperature, copper is what state? Solid, yeah. This is the temperature it would have to be at before copper started melting. 1,000 degrees Celsius. Okay? So you can melt copper, but it just takes a whole lot of energy to do that. It has to be at a pretty high temperature. Okay? And to boil copper, you don't think about boiling copper, but it's possible. It's got to be at this temperature, though. Gold. Okay, you want to boil some gold, some liquid gold, you got to get it pretty hot. Okay? Gold in the air. Oh, yeah. Yeah. Breathing in gold. Okay. Yeah, that'd be so good. Actually, if you were at this temperature breathing in gold at that temperature, you'd be in trouble. Yeah. Okay. So finally, number 5. We haven't been to number 5 yet. Let's just quickly do that. Number 5, very much the same. Yes. Number 5 is heating up the steam. Okay. It's heating up the steam. E equals mc delta T for right here, this section right here. And yes, it's possible to increase the temperature of a gas. Totally. Yeah. Did you have a question? So this is an important note here, okay? It's important to know that the total energy required to heat a sample of ice with mass m, so just like this example that we just worked through, from negative 20 all the way up to 130, that's where we would have stopped on that graph, is the sum of all energies from points 1 to 5 on the diagram. So it's the sum. Really important. So you find the energy at each stage, 1 through 5, and then you add them all up. Okay? And we're going to do a sample problem here right now, just to show you how that's done. So this first example question here says, how much energy, heat energy, is required to change, A is 2 kilograms of ice, so that's solid water, at 0 degrees, to water at 0 degrees. So we're talking about, melting, right? We're talking about melting. And so for A solution here, we're going to use the formula E equals what? MC delta T or ML? Which one? ML, yes. Because we're talking about this part of the graph right here, you see? Melting. That's what we're focusing in on right there. So it's E equals ML. Awesome. So what's the mass of the ice? 2 kilograms. Very good. Now what is the L for ice? Remember, that's a constant for water that you use in all of these calculations to be the same one. And let me just see if I can go back to that page. Where did I put it? Okay, so where's water? Here. The latent heat of, which one am I going to use again? Fusion. Very good. Yeah, you guys all said that. Awesome. So that's the number. I think that's the same one as in your textbook, correct? So 3.33 times 10 to the 5. So let's go back to that page here. 3.33 times 10 to the 5. And what's the units on that? Joules per kilogram. Now, is there a degrees Celsius here like the other specific heat? No. Why? Because we're not changing temperature, right? So that's all we need right there. Okay. So you want to make sure your units line up. So if this is not kilograms over here, then you've got an issue. But they're lining up, so that's good. They're going to cancel each other out, divide out to give you 1. What are you going to be left with as a unit? Does that make sense to have joules as a unit for energy? Absolutely. So we're doing this right. So what is this number times this number? 6.66 times 10 to the 5 joules. Or 666,000, right? Joules. All right, does that make sense to you? Okay. All right, so why don't you guys do B by yourselves? Don't look in the book because the answer's all worked out. I want you to see if you can do it by yourself without copying down from the book. Okay? Go ahead. All right, so that should be your answer for B there. Again, E equals mL. Make sure you use the latent heat of vaporization for that phase change. Okay, this is the one I want to spend the rest of our class time on here. And this one is like the graph that I showed you, right? Which is, oh, that's my little cartoon. I'll show you that later. Where's that? This graph right here. So what we're going to do is we're going to read the question, and we're going to sketch this graph first, okay? And we're going to put all the temperatures and stuff on here, and we're going to kind of lay out what we need to do. So for this question, it says how much energy is required to convert 150 grams of ice, which we know is 0.15 kilograms, right, of solid water, ice, from -14 all the way through to steam or gas phase at 106. So this is a classic example of the type of question that you're going to need to know how to do. So let's draw a little graph over here. Okay. First thing you want to do is sketch the graph, okay? Sketch the graph so you can help keep yourself organized and so you can see what's happening. So we're starting at -14. So I would suggest you starting here and writing that -14 down there. And we know that this ice is going to heat up, right? To a certain point. And what's this point? When is the ice going to stop heating up and start leveling out there? What point is that? At 0 degrees Celsius. Very good. So throw that on your graph. This is the easy part of this question. Building this graph, you should feel real confident in this when we're done. You'll see how easy it is. So what's going to happen after this is all melted after a certain amount of time? Doesn't matter what amount of time. Doesn't really matter. But what's it going to do? What's this graph going to do? Is it going to go back down? It's going to go up? What's it going to do? The temperature will rise again. And this stretch is from 0 to what temperature? 100 degrees Celsius. Very good. Right? What's going to happen to this heating graph at 100 when the liquid gas starts turning to, liquid gas. When the liquid water starts turning to gas, what's going to happen? Is it going to go down? Is it going to go sideways? What's going to happen to this graph? It's going to flatten out. Very good. So this, again, this is the phase change from liquid to gas. And then we're going to go up some more. We're going to heat that gas until what temperature? 106. Okay? Good. So this is your little heating curve sketch. And this is what you should do at the beginning of these questions. Okay? Just sketch that out. And what I would also suggest, you don't have to do this, but I think this is probably the best way to go. I would label, this section number 1, like we talked about. And I would even, if you have enough space, write out the formula for what you're going to use to calculate the energy. E equals MLF. That kind of looks like ELF, right? We're kind of coming up to Christmas here, so don't think of ELF. Oh, goodness, yes, I got ahead of myself. You're right. That was an honest mistake. I'm sorry. Good catch. That's coming next. MC delta T. Oh, goodness. Okay. Number 1. Very good. You guys are on top of things. I love it. Number 2. Let's try this again. This is the ELF one, right? E equals M L of fusion. For number 2, that's this space right here. Good. Good? 3. What's happening here? E equals MC delta T. Very good, because there's a temperature change. Awesome. 4. E equals ML of vaporization. And then 5. E equals MC delta T. I keep wanting to say Q equals MC delta T because in chemistry it used to be always that this heat was Q. Q equals MC delta T. That's the way I learned it back in the day when dinosaurs roamed the earth when I was a kid. All right? All right, good job. No, we got that right? Very good. Very good. Questions? So let's do number 1, just like we did in the notes there. I showed the notes. E equals MC delta T. Let's get it figured out. M is 0.15 kilograms. You don't have to put the units, actually, as long as you're sure that they're all going to line up. I'm going to do it for the first stage here. What is the C of solid ice? Let's go back into your textbook there. Have that page kind of on speed dial there. So water, ice, specific heat, 2.1 times 10 to the 3. And that's going to be, of course, joules per kilogram times degrees Celsius. So again, you don't have to do the units. You really don't have to do the units, but I'm just going to do them to make sure that you see everything's going to line up. And what's the temperature change here? 14 to 0 is going to be positive 14. Good, we're heating up, so we want a positive energy. 14 degrees Celsius. Awesome. So these are the numbers we're looking at here. And let's just double check to make sure the units line up. We've got a kilogram on top, kilogram on bottom. Those are gone. We've got a Celsius on top, Celsius on the bottom. Those are gone. We're left with joules. Is that the unit we want for energy? Yes. Absolutamundo. E equals. What's the product there? All those 3 numbers. Get your calculator. That'd be a good idea. I'll get mine too. There it is. 0.1. Oh, on. 0.15 times 2.1. 3. You can write that as a decimal if you want. Times 14. 4410. Did you guys get that one? 4,410. Don't worry about sig figs here for this question. Let's just get the numbers right. And joules, right? Okay. Awesome. Now we're going to keep that. Just keep that number there because what do we have to do? We have to find the energy associated with the other sections, and then add them all up at the end. Right? Okay. I'll do one more section with you, and then I won't give you any other homework other than just finishing this one. Okay? No other homework other than finishing this one. So I'll do 2 with you, and then you can do the other sections between now and Monday. Okay, so this one is E equals what? MLF. Awesome. MLF. So the mass is still 0.15. I'm going to drop my units now because I know I'm all good. And then what's the latent heat of 3.33 times 10 to the 5. Right? Okay. And you do that calculation. $49950. Did you guys get that? 1, 2, 3, 4, 5. See, I just moved the decimal place over. So 49,950. And what unit is that? joules. Awesome. Okay. So we'll keep that one tucked in our hat there too. So you guys go ahead and do. What did I write 3 there for? I'll tell you. I'm not on my game here today. So that's section number 2. Now you guys are doing 3, 4, and 5, and then adding them up. Okay. So that's your job, and you've got 4 or 5 minutes here. You might even get that done. Have no homework this weekend. Would be awesome.